Hello, my name is Chris Ford and I work for PerkinElmer. I have developed this project from a problem within the company. This problem arose mainly within the development area, but it is anticipated it could be used in the field as well. We therefore have the makings of the VME EPROM programmer. Virtually all of PerkinElmer instruments are processor controlled, even though the complexity of these vary. A large percentage of these operate in a VME bus system. This system is fast becoming the company standard. The card system has a motherboard, down here at the bottom, which has two bus systems, the standard bus and the user bus, which varies from board to board. Our first board is the processor board, which may be 68020, or in our case, the 68000. Next, the memory board, and finally the VDU board, which is necessary due to the onboard RS-232, which enables us to communicate with the terminal. With this system available, we can begin development of the EPROM programmer. Here we can see a block diagram of the stages of development. Obviously these tend to overlap a little. The analog system was designed first, as I thought this to be the most difficult and best to get out of the way. There are several voltages on the motherboard, but none of these are of high enough current of rating to be of use. It was decided that rather than replace the regulators on the motherboard, which would make the system unportable, it would have a flying lead to the power supply. Here is a block diagram to show the analog circuit. The 15 volts is increased to 28 volts through the switching regulator here. This is fed into an ordinary regulator, which feeds the voltage programming pin on the EPROM. As you can see, different output voltages are available. Both of these regulators are adjustable and can be digitally selected. Open circuit values are obtained by turning off an inline transistor. The digital part of this project revolves around the PAL, here. PAL stands for Programmable Array Logic, which is used instead of a vast number of individual gates. It is this device which controls the whole board. It controls all the analog switching, read and write operations and decoder facilities. As far as the processor board is concerned, this board is an address in memory. Therefore, all address lines, data lines and other processor signals have to be buffered so as not to overload the lines. Address lines are permanently enabled, but the data lines are operated through bidirectional buffers. Most of the time the data flows from the processor to the programmable board. There are two cases, however, when the data is required to go the other way. One of the occasions is when we need to know the contents of the EPROM. The second occasion is when we read the state of the current overflow flag. This flag is produced by part of the analog circuit. An inline resistor is used to measure the current flowing, which turns on a transistor. Apart from setting the flag, it automatically turns off the supply and turns on an LED. The flag is needed, however, so that the software can interrogate the condition of the board. The buffer direction is controlled by the PAL, and a lot of work had to be done to make sure the timing was perfect, or else bus contention could have occurred. This prototype board, which I've seen throughout the video, is only capable of accessing a 512K EPROM. The final board, however, will be able to access 128K to 8 meg EPROMs. The software for the board is written in 68000 assembler. I hope you've enjoyed this video, and I will be pleased to answer any questions that you might have to ask. Thank you.